Hello student, today's topic is simple harmonic motion or S.H.M. At first, we are trying to understand about periodic motion. What is periodic motion? When a particle moves along a circular path with constant angular speed omega, then the motion of the particle is known as periodic motion. Or in any case, when the motion of a particle repeats after some time interval, then this motion is known as periodic motion. It may be circular, it may be elliptical, or it may be linear. When a particle moves from a point to another point and comes back to from B to A after some time, then this motion is also periodic motion. Next, what is vibration or oscillation? When a particle moves along a straight line and executes a periodic motion with respect to a point or midpoint, then this motion is known as vibration or oscillation. That is, a particle moves from the point A to B, and next after some time interval it comes back to from point A B to A, and then it moves to B from A, again from B to A. This is the to and fro motion of the particle with respect to the point O. Then this motion is known as vibration or oscillation. This is also periodic motion, but this is a circular motion. Therefore, we can say that every vibration or oscillation is a periodic motion, but every periodic motion is not a vibration or oscillation. These two motions is known as periodic motion, but only this motion is known as vibration or oscillation. Therefore, every vibration or oscillation is a periodic motion, but every periodic motion is not a vibration or oscillation. I think you can understand the difference between vibration or oscillation and periodic motion. Next, what is S.H.M or simple harmonic motion? When the acceleration of a particle is directly proportional to its displacement but opposite in direction, then this motion of the particle is known as simple harmonic motion or S.H.M. That is, the displacement of the particle with respect to the mean position is directly proportional to the acceleration, but the direction is opposite to the, or displacement is opposite to the acceleration. Let us consider this is a simple pendulum. It is suspended from a rigid support. P is the point of suspension. When the pendulum is in rest, then the position of the bob is O. This is known as mean position. The position of the bob when is in rest, then this position is known as mean position. When the bob is slightly displaced, that is the angular displacement is less than 4 degree, then this bob experienced some restoring force which tries to back this bob to its original position at the point O. This is restoring force F acts on the bob which tries to back the bob at its original position, that is at O. Now the displacement of the bob is x. Since the angle theta is very small, then we can consider OA is a small line segment. Let F is the restoring force acts on the bob. X is the displacement of the bob. Now F is directly proportional to x, and we introduce negative sign because the direction of F and x are opposite. F acts from A to O and x acts from O to A. That is F directly proportional to minus x. Okay. That's how we can write, therefore F is equal to minus kx, where x is the force constant, while x is known as force constant. While k is known as force constant. Okay, k is known as force constant. If m be the mass of the bob, then acceleration of the bob is A is equal to F by m, or A is equal to minus k by m whole into x. Since k by m is equal to constant, therefore we can write A proportional to minus x. This is an example of simple harmonic motion, that is acceleration is directly proportional to displacement and in opposite direction. Okay. Let k by m is equal to omega square, where omega is the angular speed of the bob. Therefore we can write A is equal to minus omega square x. Therefore in S.H.M the acceleration A is directly proportional to the displacement and opposite in direction, that is A proportional to -x. This is the definition of S.H.M or simple harmonic motion. Let a particle executes S.H.M along the path P prime with respect to the mean position O. Q is any point on the line segment, that is P prime. OQ is x, the displacement of the particle. Now the extreme or maximum displacement of the particle with respect to O or mean position is known as amplitude of the particle, that is A. A is equal to amplitude of the particle. This is equal to OP, is equal to OP prime, that is maximum displacement of the particle from its mean position. And then what is time period? The time interval after which the particle repeats its motion. Therefore time period capital T is equal to 2 pi by omega, and frequency F is equal to 1 by T, that is reciprocal of the time period. Our next topic is relation between the circular motion and S.H.M. Relation between the circular motion and S.H.M. It is a very important topic. Let a particle moves along a circular path with constant angular speed omega. It starts from the point P, and after time t it moves at the point Q and produces an angle theta at the center of the circle. Now we draw a normal on the axis x prime x from the point Q, that is Qn is normal to x prime x, where O is the center of the circle. Let a particle moves along a circular path with a constant angular speed omega in anticlockwise direction. O is the center of the circle and capital A is the radius of it. The particle starts from the point P, and after time t it moves at the point Q. Okay, angle QOP is equal to theta. Angle QOP is equal to theta. QP, QN is normal, QN is normal to OP. X prime, X prime, O, N, P and X are collinear. Okay. If the particle moves along the circular path with constant angular speed, then the foot of the perpendicular, that is the point N, executes simple harmonic motion along the diameter of the circle with respect to the center of the circle O. That is, when the position of the particle at Q, then foot of the particle perpendicular A is at N. When the position of the particle is at the point on the y-axis, then the foot of the perpendicular is at point N. When the position of the particle is at Q1, then the foot of the perpendicular is at N1. Then when the position of the particle is at Q2, then the foot of the perpendicular is at N2. Similarly, when the position of the particle is at Q3, then the foot of the perpendicular at N3. In this way, when the particle moves along the circular path, then the foot of the perpendicular moves from P to P prime, and again from P prime to P, and again from P to P prime. That is the to and fro motion with respect to the main position O. That's why we can say that the foot of the perpendicular executes S.H.M with respect to the center of the circle. This is the relation between circular motion and S.H.M. Okay. Now let ON is equal to X is equal to displacement of the particle executing S.H.M with respect to O. Clear? Now from the right angle triangle QON, we can write X is equal to OQ cos theta. We know that radius of the circle is capital A. Therefore, X is equal to capital A cos theta is equal to omega t. Since omega is the angular speed and t is the time taken. This is the mathematical relation between circular motion and simple harmonic motion. And it is also the expression of the displacement of the particle executing S.H.M. This is the expression of displacement of the particle executes S.H.M. Okay. If another particle lags behind by an angle phi with respect to first particle, then its equation of S.H.M is x equal to a cos omega t minus phi. That is, if we consider a second particle which starts from the point P prime, and first particle starts from point P and second particle starts from point P prime, but their angular speed are same, then the displacement, then the equation of S.H.M of the second particle is x equal to a cos omega t minus phi. Similarly, if another particle leads by an angle phi with respect to first particle, then its equation of motion is x equal to a cos omega t plus phi. That is, it leads by an angle phi, then its equation of motion will be x equal to a cos omega t plus phi. Okay. Now we are going to find out the velocity of the particle executes S.H.M. We know the equation of S.H.M is x equal to capital A cos omega t minus phi, where x is the displacement of the particle, a is the amplitude of the particle, omega is the angular speed of the particle, phi is the phase difference. Then velocity v is equal to velocity of the particle v is equal to dx dt. That means differentiation of displacement of the particle with respect to time t. Therefore v is equal to minus a omega sine omega t minus phi. This is the expression of velocity of the particle. This equation can be written in this form: v is equal to minus omega root over of a square within whole second bracket 1 minus cos square omega t minus phi. And you know that a cos omega t minus phi is equal to x. Therefore we can write v is equal to minus omega root over of a square minus x square. This is another form of equation of the velocity of the particle. At the mean position, of the particle, that is x is equal to 0, we can get v will be maximum. V maximum is equal to minus a omega. At the end position, of the particle, that is at x equal to a, we can write v will be minimum and this is equal to 0. V minimum is equal to 0. Therefore at the two end positions of the particle, the velocity of the particle will be 0, and at the mean position of the particle, the velocity of the particle will be maximum, which is equal to minus a omega. Now we are going to find out the acceleration of the particle. We know velocity of the particle is v is equal to minus a omega sine omega t minus phi. Therefore, acceleration of the particle is a is equal to dv dt, that is differentiation of velocity with respect to time t. This gives a is equal to minus a omega square cos omega t minus phi. You know that a cos omega t minus phi is equal to x. Therefore, we can also write that a is equal to minus omega square x. This is the another expression of acceleration of the particle executes S.H.M. Since omega is equal to constant, therefore we can write a directly proportional to minus x. This is the definition of S.H.M. At the mean position of the particle, that is at x equal to 0, we can write the acceleration of the particle will be minimum and it will be 0. Okay. At the end position of the particle, that is at x equal to a, acceleration will be maximum and it will be minus omega square a. This is the graph of displacement of the particle. We plot the time along the x axis and we plot the displacement of the particle along OY axis. This is the cos curve. X is equal to a cos omega t. Okay. This time is t by 4. This capital T stands for time period. This point stands for capital T by 2. This is 3 capital T by 4 and this point stands for capital T. This graph shows the velocity versus time. Along x-axis we plot time t, small t, and along y-axis we plot the velocity v. This is a sine curve, a negative sine curve, that is v is equal to minus a omega sine omega t. This graph shows the acceleration versus time curve. Along x-axis we plot time t, along y-axis we plot the acceleration of the particle a. This graph represents x equal to minus a omega square cos omega t equation. Therefore, we can say that the first curve or displacement curve and acceleration curve are almost mirror image to each other. We are going to find out the kinetic energy of the particle executes S.H.M. That is, kinetic energy Ek is equal to half m v square. You know that v is equal to how much? Omega root over of s square minus s square whole square. This gives Ek is equal to half m omega square s square minus x square. This is the expression of kinetic energy of the particle executes S.H.M. Now we are going to find out the potential energy of the particle executes S.H.M. That is EP, potential energy, is equal to integration of minus f dx 0 to x. Here minus I introduced such that the direction of force is opposite to the direction of displacement of the particle. this is equal to minus integration of x a dx, while m is the mass of the particle. We know F is equal to ma, and you also know that a is equal to minus omega square x. Since omega square is constant, therefore we can integrate x only with respect to dx. The integration of dx is half x square. That is, potential energy of the particle is equal to half m omega square x. Now the total mechanical energy of the particle E is equal to Ek plus Ep, that is kinetic energy plus potential energy. You know that expression of kinetic energy is half m omega square a square minus x square, and expression of potential energy Ep is equal to half m omega square x square. That's why we can get the total mechanical energy of the particle half m omega square a square, which is equal to constant. Therefore, the total mechanical energy of the particle executes S.H.M always remain constant. This graph shows the variation of both kinetic and potential energy of the particle with respect to the displacement of the particle. Here along x-axis, the displacement of the particle is denoted, and along y-axis we plot the energy of the particle. Either it is kinetic or it is potential energy. ABC is a parabolic curve. ABC is a parabolic curve which shows the variation of kinetic energy, that is Ek of the particle, and the parabola DOF shows the variation of potential energy of the particle, that is Ep, with respect to the displacement of the particle. The total mechanical energy of the particle always remains constant. This shows this proves the principle of conservation of mechanical energy, or this proves the principle of conservation of energy. Let a bob is suspended from a strong support or rigid support. The P is the point of suspension and O is the mean position. If the angular displacement of the bob is very small, then this bob executes S.H.M. L is the effective length of this pendulum. L is the effective length of this pendulum. OQ is the displacement of the bob at any instant. Now T be the tension of the string. We can M be the mass of the bob. Mg is the weight of the bob. We can resolve the tension T along, and this is Mg acts vertically downward. We can resolve Mg cos theta along the string of the bob, which acts against the tension of the bob, and another component Mg sin theta acts as a restoring force which tries to return back the bob to its original position. This is F is equal to Mg sin theta, this restoring force. Here F is equal to Mg sin theta or minus Mg sin theta F is equal to minus mg sin theta acts as a restoring force. Here minus sign introduced for restoring force. Therefore acceleration A is equal to F by m. This is equal to F is equal to minus g theta. Since theta is very small, less than 4 degree, that's why sin theta approximately equal to theta. Okay, and from this above graph we can say, or above figure we can say, theta is equal to x by L. From circular motion we can write s is equal to r theta. That's why we can say theta is equal to x by L. Okay, since theta is equal to x by L, and again g by L is equal to constant for a particular position of the pendulum. That's why we can write A proportional to minus x. Therefore the bob shows S.H.M or simple harmonic motion. Therefore the motion of a simple pendulum is S.H.M. It is proved. Now we also know that A is equal to minus omega square x. We know A is equal to minus omega square x, where omega is the angular speed of the particle. Therefore we can write omega square is equal to g by L, or omega is equal to under root of g by L. This is the expression of angular speed of the bob. We can also know that time period of the bob or particle t is equal to 2 pi by omega. Therefore t is equal to 2 pi under root of L by g. This is the expression of the time period of the simple pendulum. Let a spring is suspended from a rigid support. P is the point of suspension. Now if force is applied, therefore the spring is extended by a small length x. Now due to the elasticity of the spring, a reaction force F is produced. Therefore the spring executes S.H.M. Therefore the spring executes S.H.M. Let restoring force is F and K is the force constant of the spring. X is the displacement of the spring. Therefore we can write F is equal to minus kx. A negative sign introduced due to the restoring force. Therefore acceleration A is equal to minus k by m into x, where m is the mass of the bob attached with the spring, and m is the mass of the bob attached with the spring. Okay, now we know that a is equal to minus omega square x. Therefore, omega square is equal to k by m, or omega is equal to root over of k by m. This is the expression of angular speed of the spring. Now, time period t is equal to 2 pi by omega. Therefore, t is equal to 2 pi root over of m by k. This is the expression of time period of the spring. This is the end of our discussion for today. I think you enjoyed my videos. Please like the video and please subscribe my channel. Your subscription encourage me to make more videos. Please subscribe my YouTube channel. Thank you for watching my video. Goodbye.